Hi, how are you? Hi. So many people connected in the past hour. This time shift was confusing for people, especially from the US. But I kept telling them when we actually meet. Lei, can you hear me?
Yeah, now I can hear.
Very good, very good.
Yeah, okay. Now it's okay. Okay.
Hi, Lei.
Oh, hey, nice to see you. Check. Okay, yeah, I think it's okay now.
Let us check the screen sharing.
Okay. So I'm gonna share my tablet.
Great. Okay, very good. Seems to work.
So it works?
Works.
Okay, very good.
If you have a way to, I don't know what it's called, present it or maximize the screen, full screen. Yeah, like
Okay.
this. Yeah.
Okay.
Very good. Nothing works. I don't remember. Have you been to Israel before?
No.
Okay.
Hi, Lee.
Hey. Hey, Dipendra.
Good to
Nice
see
to
you.
see you. Nice to see you too.
Very nice. Yeah. Where are you sitting? I see a lot of park,
I'm using the virtual background.
virtual background.
Yeah, it's a
Ah,
virtual background. It's a picture.
okay. No, I thought
Yeah.
it is the Jew in Singapore, which is very beautiful.
No, now it's about 10:30 p.m. So
Oh, yes, indeed. No, sorry, I am not thinking. 10:30 p.m. Yeah, late. Yes, okay. How are you, Dima?
Fine, thank you.
Yeah, so the seminars are going very well.
Thank you. Yes.
Yes. No, I think it's an activity which is bringing all the automorphic form people together.
We plan to continue this even after the pandemic.
Yeah, so do you know when the pandemic will be over?
Not yet. We have someone in the faculty who predicts it short term, but not long term.
Somebody who is in the audience who predicts.
No, not in the audience. In our faculty at Weizmann, but he is a computer scientist.
Okay, what does he say?
Well, short term in Israel, he only talks about Israel because people, he has an online questionnaire that thousands of people fill, and this gives some data. This gives what's called big data, which he analyzes. So short term, it goes down because we just had a lockdown. So as an effect of the lockdown, this goes. So we opened up, but so far it's fine.
So
now next week we open the schools, and no one knows what it will do because I mean it's some discrete change which cannot be analytically predicted from the past. The main thing is
when did the schools open? Last week?
No, last week the kindergartens open, and next week the schools will open.
Okay, next week. Okay.
So no one knows what will be the effect. Yes, you're right. It's time. I am very glad to welcome Lei Zhang from Singapore with joint work with Dihua Jiang on Bessel-Fourier coefficients and twisted automorphic descent.
Okay, thanks for the invitation, and I'm very happy to give this online talk. Okay, so since this is 10:30 p.m. in Singapore, so if I yawn too much, I'm sorry about that. Okay, so in today's talk, I'm going to talking about a very special Fourier coefficient, which is the Bessel-Fourier coefficient, and also going to talking about its properties and the applications. Okay, so this is based on a series of works joined with Dihua Jiang. Okay. First of all, let me give some notations for my talk. We're going to take the F is the number field, and the A is the ring of the ideals. So our G is going to, in general, the G going to be the classical group. So for the classical groups, I mean, including the orthogonal group, unitary group, symplectic group, and its double coverings. But since I'm only talking about the Bessel-Fourier coefficients in this talk, so I mainly all the theorems is in today's talk is just work for the orthogonal group and the unitary groups. And for the symplectic group and the metaplectic group, we have to use another family of the Fourier coefficient, which is the Fourier Jacobi coefficients. Okay, but the setting, all the general settings works for all of them. So, okay, sorry, can you see my slides? Yeah.
I can see your slides.
Okay, thanks. Okay, so, and in this, for the simplicity, to avoid more introducing more notation, the most cases I will only focus on the orthogonal groups, but the result is also works for the unitary group. Okay, so to define the Fourier coefficients, we're gonna associate the Unipotent subgroup and the generator characters for the stable adjoint orbits, okay, in the Unipotent combs. And those stable adjoint orbit is parametrized by the certain partitions of the matrix size for these classical groups. Okay. And let me give you examples here. This is a simple example for the for the split orthogonal group SO6. And we know the stable Unipotent orbit is parametrized by those 5 partitions. And those partitions are listed in the topological order, which means this is the biggest one corresponding to the regular orbit. And 1 to the 6 powers, the power is referring to the multiplicity, and that is the trivial orbit. Okay, so that's roughly the meaning of the partition. And you see the right one, this partition is gonna give us the Bessel-Fourier coefficient, which is we're gonna discuss into this talk. Okay, and once we have a stable Unipotent orbit, we also can pick up the rational orbit. And for each rational orbit, we can associate the Unipotent subgroup and the non-degenerate characters. So we have learned we will not discuss the general settings, but only focus on the Bessel-Fourier coefficients. I think for the general settings, for other examples, we also learned from the Dima's early talk and also Bai-Yin's talk. So today I'm gonna only focus on this very particular one, and for the Bessel-Fouriers. And once we have a unipotent subgroup and the characters for the automorphic form on the group G, we can define the Fourier coefficient of the phi by taking the integrations on the quotients on the unipotent subgroups against with the character. Okay, so we define this integration gonna produce a function, and we call this is the Fourier coefficient of the automorphic forms. So that's the general definition. Okay, let me show you one simple examples here. If we take the O is the Unipotent orbit is the regular, the biggest one, and this is going to give us the Whittaker coefficients. And of course, this is defined over F only when this is a Cauchy split groups. Okay, and for our Bessel-Fourier coefficient, also called the Gelfand-Grieve coefficient, and which is the for the orthogonal group and the unitary group, and combine them together, I'm going to call this is a Hermitian type of the classical group. And for this Bessel-Fourier coefficient is corresponding to this partition. So this is a legal partition for the orthogonal groups. Okay, and similarly, for the skew Hermitian type, which means the symplectic group, SP tilde, and the unitary group. So we're going to take the Fourier Jacobi coefficient, and they are corresponding to this partition. And in that case, we may also to involve the Wee representations here. So to define the suitable Fourier coefficients. Okay, so this is the general setting. And next, I'm gonna elaborate more details about these Bessel-Fourier coefficients for these partitions. So let's see for this partition, what kind of the unipotent subgroup and the character we can associate with. Okay, let's see. Okay, so for the orthogonal group, we take this quadratic space first, whose dimension is n. And the quadratic space is defined given by this symmetric matrix. A symmetric matrix is size is n by n. And inside of the middle block is the diagonal matrix. We allow this spaces maybe not the corresponding orthogonal group maybe not quasi-split. Okay, it could have a non-trivial isotropic kernel. Okay, so that is our quadratic space, and we take the G special orthogonal group. And for this partition, okay, we're gonna take this unipotent subgroup. Sorry, we're gonna take this unipotent subgroup based on this given quadratic forms. The matrix we chose is here, and this is roughly a upper triangular matrices. And this Z is in the block of the size L, which is the standard maximal unipotent subgroup, which is the upper triangular matrices. And the Y and X could be arbitrary. And here the Y prime and Z star, they are just determined by Z and Y. Okay, so this is the unipotent subgroup we take. And this ZL is referring to the standard maximal unipotent subgroup for the general linear group. Okay, now let's see the corresponding Levy subgroup. Okay, so for the corresponding Levy subgroup is, we have this part is lived in the GLL. This is the set of the GLL, and they are lived in the diagonal entries. And this SOW is corresponding to this middle block here. And this is the Levy subgroup normalized this unipotent subgroup. And our dimension of this subspace W is just the n-2L. Okay. And now let's associate the non-degenerate characters. For the non-degenerate character, we pick up an isotropic vector instead of the W. Okay. And this isotropic vector can help us to construct an F rational nilpotent orbit instead corresponding to this partition. And we define the character on this unipotent subgroup just by taking the first part. This is coming from the matrix Z. This is like our regular weighted coefficients instead of the GL block. And the second part is for this Y block. And the W0 is our fixed isotropic vector. And the YL is the bottom row of this matrix Y. And we also can identify it as a vector instead of space W. So this inner product is coming from the restriction of the quadratic forms. Okay, so this is the non-degenerate, one non-degenerate characters. And of course, you may take the different isotropic vector. You could get the different F rational nilpotent orbit. Okay, we may have a different pairs here. Okay, so our Bessel-Fourier coefficient is roughly associated to this pair. Okay. Okay, and let's see for such a character, we have the Levy subgroup here is acting on this because this Levy subgroup is normalizing this unipotent subgroup. So it's also acting on this character by the conjugation. And if we let this Levy subgroup acting on this character, and we may talking about the stabilizers and so on. Okay, so we're gonna denote this GOL to be the stabilizer of this action. Okay. And just one more remark. For this, originally, when we fix the partition, we only get a stable Unipotent orbit. And once we choose the anisotropic vector W0, we get the rational orbits. And if you want to pick up all the rational orbits in this stable Unipotent orbit, we always can do that by choosing a suitable W0. So that is quite elementary linear algebra calculations. So in other words, by choosing this W0, we can exhaust all the possible rational orbits here. Okay, and now let's come back to these stabilizers. And for this stabilizer, this is going to give us the subgroup for the Levy subgroup. And instead of the Levy part, the GL1 block is to fit, in order to fix the W0, the GL1 part is going to be trivial. And for the SOW part, we get this subgroup, which is fixed the vector, isotropic vector W0. In other words, you're going to preserve the complement space of the W0. So that is our stabilizer. I'm taking the connected component here. Okay. And the matrix size, originally this W have the dimension, which is the n-2L, but we removed the one dimension here. So the matrix size for this stabilizer is going to be n-2L-1. And you may realize that this has a different parity with the original group. So if we have stuff from the even orthogonal groups, this stabilizer is going to give us an ordered orthogonal groups. And if we start from the ordered orthogonal group, we're going to get an even orthogonal group. Okay, so this is some preparations for the Bessel-Fourier coefficients. Okay. And now let's using this coefficient to construct the representations or to get the automorphic descent. Okay, so this is, we just apply our general Fourier coefficient for this particular case. We have this automorphic form, integral over this Unipotent subgroup against the characters. So I'm going to use this curly F to denote this Bessel-Fourier coefficients. Okay. And as we see, if we run over the H instead of the stabilizer, because this is fixed the character and the phi is automorphic, so the function we produced on the GO on the stabilizer is also F rational point invariant. So this is going to give us an automorphic functions on the stabilizer. And if we let this, let the stabilizer do the right translation on this function, this is also going to help us to produce the GOA modules. And this is the Ginzburg-Rallis-Soudry introduced, which is the automorphic descent for such pi. Okay. Okay, so when we're talking about the automorphic descent, we are usually referring to the space produced by these Bessel-Fourier coefficients on the stabilizer.
Sorry, may I ask you a question?
Yeah, sure.
In your definition of autom function, you mean autom form satisfy G finite and K finite?
No, we haven't move to that step yet. So of course, if you have to put the generally for the automorphic forms and going deeper, we can prove that, but not at this moment. This is just at this moment, it's just a general setting. So I only claim this is a module and it's a function. I haven't claimed this is the form. Yeah.
I see. Thank you.
Okay. Okay. And the one more remark I would like to emphasize is the non-vanishing for this coefficient is also depending on the choices of this rational, the isotropic vector, which means if we choose a different W0, we may get for some W0, for some rational orbit, it could be vanish. For some, it could be not. So this is depends on the choice of this rational orbit. Okay. Okay, now let's explain what is our motivation and what is the question we're going to ask for those automorphic descent. And the first thing is we can verify the L. So if we verify the L, we may get the size for the stabilizer may be different. And when we verify the phi, we may get a modules for the stabilizers. Okay. So this is just to indicate that we change the different L, we choose the different depths for these Fourier coefficients, we may get the modulus for the different groups. And here is our two questions we can ask regarding to this automorphic descent. The first question is related to the branching problem, which means if we start from the pi, we get a new representation or new modules for the stabilizers. And the question is, how do we understand the automorphic descent in terms of the Arthur's endoscopic classifications? Okay. In the other words, what is if we fix the representation on the G, we're going to produce the representation of the on the H. So it's natural to ask what kind of the representation of the H occurs here in this restriction. So that's a classical branching problem. And another problem is we can ask reversely, which means the reciprocal branching problem. And that means if we fix the pi, still the pi is on this G. We take the G as the stabilizer. And the H is a bigger group, contains G. And we may ask if we fix the pi, what kind of the representation of the H contains such pi? So this is the reciprocal branching problem. And the second way is can help us if we can construct such representation on the H. This is can come back to help us to understanding the pi. So we're going to see some precise applications or discussions later, very soon. Okay. And now let's focus on the first question, the branching problems. Let's see if we vary the L, what's going to happen and what can we say? Okay. So I'm taking the orthogonal group as an example. This is the Tor properties proved by Ginzburg-Rallis and Soudry. We pick up cuspidate automorphic representations here. And when we produce the models, this is for the orthogonal groups. The size is n-2l-1 is depending on the choices of the L. If we vary L in this list, and it could have something like a bunch of the zeros if you take the L is bigger. But at a certain point, the first non-zero space is always going to give you a cuspidate automorphic representations. And we're going to call such L0 is the first occurrence indexed. The first occurrence indexed. Okay. And this is only non-zero for some W0. Okay. Just the one W0 is good enough. And above that, you're actually going to have the space is no longer zeros. But the first guy is the first occurrence one. Is always have nice properties here. Okay. And we're gonna ask the following another two questions regarding to this first occurrence indexed. Okay. So the first question is this first occurrence indexed L0. This is a natural number, at least the non-negative integers. So the question is, if we given the pi, can we determine this L0 in terms of this pi? And if we have the pi is given by an Arthur parameter, and given by the Arthur parameter, how do we know this L0 in terms of this Arthur parameter and so on? So that's the first question. And the second question is, at the first occurrence, we know they're going to have some rational orbit. The descent is not equal to 0. So what are the automorphic representation occurs here? and what are their corresponding other parameters. So this is kind of like the refined the branching problems especially at this first occurrence indexed. Okay. And also, of course, we're going to have the local analog version. And in the local version, we may replace the Bessel-Fourier coefficient by using the degenerate Wittig models, or also called the twisted Jacobi models, to discuss the representation is produced on the stabilizers over the local fields. Okay. So this degenerate Wittig model is also discussed in a little bit in Dima's talk, so I will not take you through the details here. Just to give you some flavor to see what we can expect for the local analogous problems. Okay. So in these slides, I'm going to take the nu is a finite place. The F nu is the corresponding non-Archimedean local field. Okay, and here is what we can say at the first occurrence indexed. So we assume that pi nu is in the generic Vaughan packet. Okay, so because this is the packet is the union for not just for the quasi split, but all the pure inner form. So we take the local Vaughan packet here. Okay, and this packet contains the generic representation. So this is we call it the generic Vaughan packet. For each, so let's say if we have a rational orbit, the local descent of pi at this first occurrence indexed, this is going to give us a representation for the smaller rank of the orthogonal groups, which is going to be either 0 or if it's not 0 for some rational orbits, it's always going to be a direct sum of squared integrable representations. So at the first occurrence, it's always square integrable representation. This cannot be too bad. Okay. And of course, it's multiplicity free because we have the multiplicity 1 theorems. Okay. And the local multiplicity 1 theorem is proved by Dima. So that is how do we get this?
What do you assume on phi?
Sorry,
what did you assume, what did you assume on phi on the parameter?
What is
what did you assume on the parameter phi?
The phi is the generic parameter.
It's elliptic. It's what?
The generic, I mean, this packet contains a generic representations. In the other words, is always can be expressed as the standard modules, irreducible standard modules.
But is it elliptic?
It's elliptic. It contains elliptic. Okay. Okay, so that's the first part. And the second part is quite combinatorics, is we give an algorithm to write down the corresponding L parameters or the given in terms of the local lines correspondence to get this the representation occurs in this local descent. So I'm going to give examples for the even case. In our paper, we also give for all the orthogonal groups, but here the even case is relatively easier to stay. Okay, so this is the part for the local descent, and it's coming from this direct sum. And this is the representation given by the corresponding local lines correspondence. And I probably will not explain all the notations in this theorem. I just give you a flavor to explain what are we able to nail down for the descent. The first of all, about this rational orbit, the W0, we actually can get explicitly compute this which rational orbit can show up based on using the long lines correspondence and also the local Gangros-Prasad conjectures. So that means this alpha A is referring to how do we fix the choices of the Wittig how do we choose the weighted data to fix the local Lorentz correspondence? So that is the A coming from. And the discriminant for this orbit is to defined by the discriminant of the stabilizer space. So this W0 is defined coming up from this bunch of the equations is determined by the compatibility of the data. And by giving start from the phi, oh, sorry, this is my fault. I have to say this is another phi. Okay, so this is the phi for the pi, and the phi chi is the corresponding L parameters for the pi, the Lorentz data. And we may define the descent for the L parameter side by using the local Gangrosprasad conjecture. So by the explicit computation, we can give a roughly description to what kind of the descent parameter is going to show up for the L parameters. In other words, the corresponding representation is going to show up by using the local GGP. So this is how do we describe the representations occurs in this descent. Okay, so this is roughly we can say about this descent. And the key ingredients, of course, is this local Gangrosprasad conjecture and also the explicit computations of the local symplectic roots. Okay, so basically the question we're asking here is if you fix the one parameter and you run another choices to looking at the local symplectic root of this tensor product to say ask when it's going to equal to -1. Okay, so that is the question we faced. And also we have the general cases, which is for the unitary group case and also the Fourier-Bessel case, Fourier-Jacobi case. And this is an ongoing project with the Dongwen Liu in the Zhejiang University. Okay. And the reason we are quite interested about this first occurrence is because if we have in the generic Vaughan package, we conjecture this first occurrence, the largest P1, oh, I missed this part. The largest P1 is equal to 2L0 plus 1. Okay. So the largest part in the partition, so as this partition, I'm listed them in the decreasing order. And the P1 is equal to the 2L0 plus 1. And the L0 is the first occurrence index that we see in the previous slides. And this partition is the top partition is associated to the representations. Associated to representation is pi, which means like the largest partition according to the topological order, such that associated degenerate weighted models are non-zero. Okay. So we put all those partitions together. That is give us the set p pi, and this conjecture is just to say the largest part is coming from this first occurrence index. Okay, so that is to get the information for the first piece. Okay, and this index for some cases can be computable from the L parameters by computing the local symplectic roots. Okay, so that is the roughly picture for the local analogies. And for the globals, we don't have so precise result like this or conjecture like this. Okay, so let's move to the global part for this problem. Okay, and for the global part, there is approach is.
Can I ask you a question?
Yeah, sure.
You know, you said that the first occurring index is a direct sum of discrete series representations.
Yes.
Is it a finite sum or infinite sum?
No, it could be, we cannot prove it's finite at this moment. I think it's possibly infinite, but for some cases it's finite.
Or is it just one representation?
Oh, it could be. Like, for example, if you have the unipotent representation, this could be only unique. This could be irreducible.
So there are cases in which it is more than one?
You mean, what is more than one?
You know, this direct sum is over several representations.
Yes. Over this direct sum could be it could be infinity. We didn't exclude that. This is for the first. In general, I expect that the most cases should be finite, but we haven't. We didn't prove that. We haven't proved that in this result.
In the first occurrence where it is direct sum of square integrable, it may be finite or it may be infinite.
Some cases, for some cases, we do know it is finite, but we don't know if it's finite for all the representations, for all the representations in the generic packet. That is, we don't know.
Okay, good.
Okay.
All right, thank you.
Okay.
Let me ask you another question if I may.
Yeah, sure. Yeah.
I couldn't pass, if you go the next slide.
This one?
Yes, I couldn't pass the sentence. The conjecture.
This sentence?
Yes.
So this sentence means I'm define this p pi is like the view front for the pi. I'm take the largest partitions in this view front.
Yes. Okay,
so for this set is a collection of the partitions. Yes. And for the conjecture says like if we have a partition in this set, we can write the partition in this way. And its conjecture says this first part, the largest part in this partition, is given by 2L0 plus 1.
Oh, I see.
Okay. Yeah, sorry, I missed the 2L0 plus 1 in my statement. Yeah, it's computed from this first occurrence. Yeah. Okay. So now let's see the global case. And for the global case, one way to study what is the spectrum of the automorphic descent is we do the projections, which is we do the integrals for the representation in the stabilizers. And this is the Fourier coefficient we produced, and we integral against with the phi sigma, another automorphic forms on the sigma. So we started this Bessel period. We started this integral to see when it is not 0 or equal if it's 0. And of course, in general, this is you do have some convergence issues, but if you have one of them is cuspidal, this rapid decay should be okay. But if you have two Eisenstein series or more complicated case, we have to regularize it. Okay, so that's another story. But in today's talk, the most cases, all the cases we involved is at least one of them is cuspidal. So this is the Bessel period. And sorry, I probably, yeah, okay. Let me come back here. Okay. So yeah, now let's see the corresponding global question. So if we take the pi is a cuspidal, and following Ginzburg-Rallis-Soudry's result, and we know this part is also in the first occurrence, we're going to have this is cuspidal automorphic representations, and combined with the multiplicity 1 theorem, and we're going to have a multiplicity free decompositions at this first occurrence, which is nice. And but it's hard to see what kind of the sigma occurs here. So we make one conjecture here is give some hope to shed some light for this answer. If we take the pi is of the tempered Arthur parameter, which means almost all the unramified part is generic. So that is the assumption we put on the pi. And if we assume this is at the first occurrence, okay, it's non-zero. This is the first occurrence rational orbit. And at least one of these sigma should be also have the tempered Arthur parameters. Okay. And of course, the corresponding Bessel period going to be not zero. So this is we call the generic summand conjecture. It's probably all of them are in the tempered parameters, but we didn't expect that much. We only say one of them, at least one of them. So we later when we see most result, for some cases it's easy to verify, but for the general case it's still quite hard. Okay, so this is rough ideas, and also the reason is because if we use the one direction of the GGP, we know if this Bessel period is not equal to zero, and we're going to have a central value of the non-zeros. But itself, the non-vanish twist central value is already not an easy question. So we're using our studies for the Bessel-Fourier coefficients to show, for example, if I have a generic representations for the U4, and we definitely can find characters. There exist characters for U1 such that the central value is not equal to zero. And we don't have like a source result to have a quadratic character here. We don't have that strong result. It's just GL1's U1's automorphic representation. So that's we require to lose conditions for the U1 part. The idea is we actually using the Ginzburg-Rallis-Soudry exchange root lemma and get the Bessel-Fourier coefficient is not equal to zero. At least one is not equal to zero. And then we get the Bessel period is not equal to zero because now it's integral against the character. Okay. And if the Bessel period is not zero, by using the Gann-Gross GGP, we get the central value is not equal to zero. And the interesting point of this theorem is the rank of this pi is quite high. So if we can have a general rank like U2n or U2n plus 1, have a non-vanish twist is also very interesting result. Okay, so but so far, this our calculations only works for this U4 at this moment. Okay, so that is the connections why the connections with the spectrum of the automorphic descent, okay, to construct this non-vanish twist. Okay, and in the rest 20 minutes, we are going to show you how do we using the reciprocal branching problem to construct the automorphic representation, which is the second part of my title is the constructions, the twisted automorphic descent. Okay, so the idea is the question is if we have a given a Arthur parameter, let's say the temporal one or even in general, and can we construct the space of this automorphic representation? So it's got a concrete modulus. And this picture is explain the general ideas. The idea is that our machines how to do this construction. But I'm going to explain all the notations in the later slides. But here, roughly the idea is in this Vaughan packet, we have a pi in this Vaughan packet. And here the phi is also the tempered Arthur parameter. And we construct, we take like the reciprocal branch, which is we find a small representation on the bigger group and hope to do the automorphic descent to produce, to recover this representation pi. The advantage for that is what we input here is the automorphic form from the general linear group and the smaller ranks of the orthogonal group, and to produce the functions defined over the desired group G. So that is roughly our goal. Okay. And in these pictures, we also involved the Bessel period for the sigma 0 with a pi. So that is not equal to 0 to guaranteeing this Fourier coefficient is not equal to 0. Not the L0 going to be the first occurrence. Okay, so that's the general picture to explain our approach. Of course, this picture is an extension of original Ginzburg-Rallis-Soudry's automorphic descent method. So in their original method, there is no such sigma 0. Okay, and the sigma 0 is on the trivial group. And of course, they have more different extensions like Tsai, Friedberg, Ginzburg, and Kaplan's work for using the covering group to get the doubling constructions, to get the tensor L functions, and also the recently Ginzburg and Rallis' double descent is also the different
Ginzburg
way.
and
Yeah, sorry.
Ginzburg and Soudry.
Did I make some mistake here?
Rallis died more than 10 years ago.
So the Ginzburg-Soudry double descent.
Oh, yeah. Sorry. Yeah. Yes. Yeah. Yeah. Ginzburg-Soudry is the double descent. Yeah. Okay. Okay. And now let me explain and the more details about this picture. Okay. So let's see. This is the residue of the Eisenstein series is on the bigger group H. And now let me explain what is our H here. So the H, I'm taking the quadratic space. The dimension is this, 2a plus m. And we are going to assume the Witty index is at least a, because I need this parabolic subgroup whose levy is isomorphic to GLN cross m. And for the GLA part, we take the isomorphic sum. Okay? They are different. And in order to give us the source for the other parameter. Okay? And the sigma is the cuspidate representation for the smaller orthogonal groups. And using this data, we can construct the Eisenstein series. And if we assume that sigma is also of the tempered other parameter, and we can control the pulse of the Eisenstein series. So it only have two possible pulse. One is in 1/2, the other is 1. Okay, so at the point of the 1/2 is the residue we're going to use. And we're going to use the residue at this point. And the reason is this is going to provide us the correct other parameters. And you're going to see the central value non-zero here. Okay. Okay, so this is the properties for the Eisenstein series. And using, now we can consider the Bessel period involved this Eisenstein series. Okay, so we have roughly in general, we can construct two types of the integrals by considering the size of the matrices. So for one case is like what we see from the modular constructions. We take the G is the stabilizer, H is the bigger, okay, and the L is take this form. The reason is because if we take the L is like this, denoted by like this, and the size of this one is matched with our original notation, the previous notation. The size will be just n. And in another way, we can take the H is smaller. So we put Eisenstein series here. So the cuspidate is on the G. So if for this our notation, the Fourier coefficient always take in the first variables here. So for the first variable, the group is always bigger. And this is the two type of the global zeta integral. One type is we put the Eisenstein series on the bigger group, the cuspidate representation on the smaller one. And also we can take the cuspidate on the smaller one and Eisenstein series on the, the cuspidate is on the bigger one, the Eisenstein series on the smaller guy. Okay, so either way, this Bessel period is going to give us a Euler product. And if the inside the model, the inner smaller Bessel period for just for pi and the part of the Eisenstein series sigma is 0, the whole thing will be equal to 0. Okay, so that is the key properties for this global zeta integral. And of course, we can compute the L functions here. Okay, so the L function is give us this tensor L function. And this computation is based on the Soudry's early works for the orthogonal split orthogonal groups case. We just extend for all the Hermitian types. And in Soudry's case, in Soudry's computation, he also reduced to the computation to the generic case when the pi and the tau are generics. Here we don't need to assume the pi has to be in the generic package. This is just true for the general data. And for our case, for the other like unitary case and all the other cases, is also by using the Soudry's method, is also can reduce to the generic data, and which is based on the Kaplan's work. Okay. And so after using the help of this identity, we can get, and also the analysis of the Bessel period, we can get the one direction of the GGP. And so which is if you have the Bessel period is not equal to 0, the L function is not equal to 0. This is the bridge between these two results is actually the Eisenstein series have a non-zero residue at the S equal to half. So that is how do we see this L function is not equal to 0. Okay, so this is for one direction, but it also works for not just for this Bessel case, it also works for the Fourier-Jacobi case. Okay. And here is the list for the known result for the GGP. And Raphael is already give us the talk to introduce his work. And there are many cases, like also the Ginzburg-Rallis-Soudry and Ginzburg-Rallis-Jiang's result for the some generic case and the unitary case and so on. Okay. And also the local GGP case. Okay. Okay. And the max result for the non-tempered case, but non-tempered GGP. And also Julian's recent result for the Archimedes orthogonal case. This is for the strong multiplicity one, not the full GGP. Okay, so these are some known result. Okay, and now let's go back to see our constructions. Okay, so now all these notations here are introduced. So let's see this construction here. So this is the residue. Okay, so this is the residue of the Eisenstein series, and I just list in the second page following this theorem here. And this tau is again the isomorphic sum for the general linear group, and the sigma, I'm going to assume the sigma of the tempered parameter in order to control the pole of the Eisenstein series. And we're going to have those results to discuss the automorphic descent, the else automorphic descent. So for simplicity, I'm going to take the M, assume M is even. So in other words, this pi is going to live in the all orthogonal groups. So if we take the L, the depth or the for the automorphic descent is too big. In other words, the stabilizer is going to be small. Then this is all going to be automatically equal to 0 by simple local reason. And if you take the L equal to the half of M minus 1, and you may get something non-zero. And in this case, we have this direct sum. This is the possible first occurrence. And if it's not 0, every representation here going to have the other parameter, the same other parameter coming from the tau. Okay. So in other words, by using the weak long length lifting, the pi are going to corresponding to the tau. Okay. Okay. So this is now down to this descent should occurs in the desired Walgen packet in this Walgen packet. Okay. And if we assume this L is the first occurrence, and then we're gonna have it actually only contains one member by assume the local GGP here. The full we only need to assume the strong multiplicity one in the Walken packet to get these unique members. Okay, and of course in general this guy actually is not irreducible. For example, if you have, say, I put a remark here, if you have a star from consider the even orthogonal groups, and it's actually irreducible with respect to the O orthogonal group, not the, in general, probably not for the special orthogonal groups. Okay. You may have the two pieces here. Okay, and for the unitary and for the orthogonal, we all have this kind of the result. So this is to explain the isomorphism here. But this is also the sigma zero, the choice here is given by, we have to choose this sigma zero such that this Bessel period is not equal to 0 in order to produce this pi. So that is the assumption we put here. Okay. And if we assume the generic summand conjecture, okay, and that means n pi, you always can have such sigma. And n pi in the tempered Arthur parameter or in this generic Walken packet always can be constructed by run through this diagram, because we have there are at least one choices for this sigma 0 providing from the generic summand conjectures. Okay, and for all this part of the result, the descent and the one direction of the GGP for the Fourier-Jacobi case, this is an ongoing project with joined with buy-in. Okay. So our approach is also should work for all these classical groups we mentioned at the beginning. Okay, so that is the main part, and I'm going to take a few minutes to talking about the non-tempered GGP case, but is for that case, we're going to assume still need one representation is of tempered Arthur parameter. For this case, for example, this pi, I mean, interesting about this Bessel period, still the pi is bigger, the sigma is smaller. So if we assume the pi is tempered, and the sigma is for the stabilizer. Let's say, for example, the sigma in the general, the sigma could have the Arthur parameter like this. This is the general form. I just split it as the even part and the odd part. This the thing in the bracket is referring to the Arthur's SL2, the dimension of the SL2 representations for the second coordinates here. And the result is just to tell us if you have the pi is tempered, so that means this SL2 part is just 1. And if this Bessel period is not equal to 0, the phi sigma occurs in the else automorphic descent. We do have the constraints for the Arthur parameter of the sigma. You see, this still have the odd part, and for the odd part, it has to be tempered. And for the even part, it at most 2. And the GLN part, the irreducible part, which is the Kc1 goes to Kck, this part, they are actually coming from this eta, they are coming from the pi. So I'm using the same color to indicate this Kc is coming from the same colors. Okay, so this Kc1 goes to Kck is a subset of the eta 1 goes to eta s. So this is the match with the Gangros-Persalis conjecture for the branching problems, the non-tempered GGP. And vice versa, if you have the smaller guy is tempered, okay? So I'm still calling this is pi. The pi now is on the smaller guy. So it's still tempered. And the sigma is a bigger one. So let's see, this is kind of like the reciprocals. If you have the fixed pi, what kind of the sigma such that pi occurs in this sigma? So this part is similar. So if you have the odd part, it's always 1, and the even part is coming from the same colors. So the delta 1 goes to delta L, is a subset of the zeta 1 goes to zeta s. Okay. Okay. So this is all the patterns. If we just combine all of them together, okay, and that is so-called the relevant. If we assume one of them is tempered, we assume the basal period is not equal to 0. The previous discussion just to confirm those two parameters are relevant in sense of Gangros-Prasad's definition. And also this is L functions given by conjectured by is non-zero at s equal to 0, conjectured by GGP. And the only difference is we have these extra technical assumptions. This is assumption is coming from the equations like here. It's just we just trying to avoid those L functions will not give you the and will give you some extra zeros at the 1/2 point. So this is the technical conditions we haven't removed. So we assume the extra part here to get those L function is not equal to 0. Okay, so that is the one case for the non-tempered GGP. Okay, and the assumption is the significant assumption is here. At least one of the parameter is a temper, and the form is cannot. The other parameter is not that far away. They are relevant. Okay, so thank you very much, and that is the end of my talk. Okay.
Thank you very much for the beautiful talk. Questions, please.
Yeah, if I may, just one slide earlier, you mentioned that delta 1 up to delta L is a subset. I wanted to ask, is it do you have anything more precise to say? Which subset or any or?
It could, I think in general, any cases could happen. So this is the necessary condition. So it's because here I don't have any other, say the sigma could be the parameter have any other constraints. So it could be one of them, could be two of them.
I think the point is
Okay.
this L is not the first occurrence.
Yeah.
Can you go back,
sorry. Yeah, I forgot to say.
Can you go back a couple of slides?
This is the general. The L is the general. It's not necessary. Yeah, not necessarily the first occurrence. Index. Okay.
Can you go back a couple of slides, please?
Which page?
Go up.
Going up. Okay.
Yes, here. Yes. Stop. Okay. Thanks. So can you just repeat? It was too fast for me. I'm an old man. What is tau sigma is about?
Here, the tau is the isobaric sums for the GLA, general linear groups, and the sigma is just an cuspidate automorphic representation of the tempered other parameter. Okay, so that is the sigma.
Tau is a generic other parameter.
Yeah, the generic other parameters. And so for any such tau and sigma, we can consider this L's descent. If L is big, the descent is going to be 0. If the L is cut at this m minus 1, the half of m minus 1, So in that case, the G is going to be exactly on the SO2A plus 1. So in this case, the stabilizer is just SO2A plus 1. And those pi 1, pi 2, they are the automorphic representations of this SO2A plus 1. And the other parameter going to be the symplectic form, which is coming from this GL2A.
May I ask a question?
Yeah, sure.
It seems that you are interested in the first occurrence of global descent and local descent. I'm wondering, what about the second occurrence or third occurrence, such things?
Okay, so if in the first here this okay, in the first occurrence, usually we have a clear spectrum, and in the later, if the descent is smaller, you may have more complicated, like the continuous spectrum, or this spectrum going to evolve, and also it's usually expected is not equal to 0. It can be constructed from the first occurrence.
Is there a precise procedure to construct such a later occurrence from the first occurrence?
No, I think the reason is you have the result is probably too complicated. Yeah, you can construct some of them. If you want to exhaust all of them, I think the result is probably too complicated.
It is possible complicated, right?
Yeah.
I see.
So here in this result, there's no assumption tau is general, right?
Yeah, tau is general.
So just the even case, but and the even case is just technical, right?
For all. This is actually for I mean, our series for general. For even is I'm trying to avoid for the other case we have to discuss more cases in sense of the type of the other parameter, the orbit and the outer involutions and so on.
I also have a question about your conjecture from 2018 about the first occurrence.
Yeah. You mean the local one, right?
The local one.
Yeah,
so you say that P1 is 2L0 plus 1. In particular, P1 is odd.
Yeah, a particular P1 is odd.
Can you give an explanation why it has to be odd?
For this odd is referring to this Bessel. For this case, we only talking about the orthogonal group case here. For the we're not talking about the general case. It's only the representation is the generic Vaughan packet. Okay, so in the other words, this pi is coming from can be written as the irreducible standard modules. And basically, the other cases can just reduce to pi is say square integrables, the discrete case. And for that case, if you have the P1 is like the even, that is really referring to the Fourier-Jacobi models. And for this case, we do believe if you have the constraints on this pi, it should be raised up into the other part as the largest one to get the non-trivial Bessel-Fourier coefficients.
So You say that you can use Fourier-Jacobi models to show that there is actually a bigger partition.
No, I mean, this is we expect is we haven't proved this conjecture yet.
Mm-hmm.
Yeah.
But you expect there to be a bigger partition.
Yeah. I mean, in general, if you have a non-tempered, no, for the
this pi is tempered.
So for this pi is not necessarily tempered, but it's like it can be written as a induced representation from like the block is middle is the tempered, but the GL part it could be lived in the positive well chambers.
Mm-hmm.
So it's probably not tempered, but the wave front can pass to the tempered guy, pass through to the tempered induced data.
Mm-hmm.
Yeah, so that is the part we assume this is in the generic Vulkan packet. So that's the assumption.
Mm-hmm. I see. And for tempered representations, there is a restriction on wavefront.
Yeah.
I see. I see. Thank you very much.
May I ask one more question?
Yeah, sure.
Wait, in your 2020 paper with Professor Dihua Jiang, you proved one direction of a global GGP.
Yeah.
Then I'm wondering, can you extend this result for globally general representation instead of a tempered representation? Because by the Ramanujan conjecture, global
okay,
general
so
representation.
this is actually, sorry, I think this is my fault. Is I say the tempered A parameter, I really mean the generic A parameters. So we didn't using the Ramanujan, or we assume that every local place is tempered. We didn't using that assumptions. So this is for the generic A parameters. Yeah, I think the theorem is here. Yeah.
Oh, I see.
So sorry, this is the generic.
Thank you very much.
Okay.
Are there any further questions? Okay, then. Thank you again. Thank you for staying so late.
Thank you. It's okay. Thank you. Thank you very much. And it's good I didn't fall asleep.
I have one question.
Sure. Yeah.
When are we again meeting in Singapore?
I think as long as you are okay, welcome. And welcome all of you. I think so far we are doing quite well. And I think all the foreigners only need like at most 2 weeks quarantines. So I guess when we have a better environment, like a pandemic-free environment, like we can travel by, it's safe to take the airplane. Very welcome to visit Singapore again. I'm very glad to host.
Great, and you are welcome to visit Israel physically.
Sure.
Now that you have been here virtually. So I wanted to say that I noticed that there is one last slide with a proof.
Yeah, I think I have 2 slides to prepare in case about these propositions. Yeah, I think I stopped at a very good time, so I didn't go through the detail to prepare in case anyone asks about the proof.
So maybe you can say just a couple of words on those 2 slides so that they are not wasted.
I think it's okay. It's quite technical, so that's the reason I removed from my.
All right, then those interested
you already can see.
Can read them.
Yeah.
Very good. Very good. Thank you very much.
Yeah. Okay. Thank you. Okay. Thanks for the invitation, and thanks for organizing so wonderful seminars. Okay.
A pleasure.
Okay. So bye.
Bye.
Bye. So next week we have a talk by David Soudry, also on some related topic, I guess. And since the US will pass to winter time, it will be as usual for the US participants, but for Singapore participants, it stays like today. Too late, I apologize. And now this talk was not automatically broadcasted, but if Lei will permit, I will put the recording.
I'm not sure how it's going. What do you think?